So it's now my pleasure to introduce to you our presenter. He has a PhD in computer science from the University of Maryland, College Park, and he participates in many organizations and as the chair and co-chair of many technical programs. He's received the National Science Foundation Career Award in 1997 and is a member of the Networks Research Group at Boston University. And we're so glad that he has agreed to take some of his precious time and talk to us today about managing a virtual network function using SDN and control theory. It's my pleasure to introduce to you Abraham Matta. We'll turn the time over to him.
Oh, thank you, Ben. Let me start my presentation here. So thank you all for coming and to this webinar. So this webinar, as you can see from I've seen from the abstract, related to network function virtualization. So the idea here is that we can leverage virtualization now to run network services that used to run basically on what we call middle boxes or network appliances. We can run now these network services in virtual machines that can run anywhere, potentially on anywhere on the internet, possibly provided by third parties as well. Virtual network functions we are thinking about here could be a load balancer, could be an intrusion detection system, firewall, etc. So the idea here is that if you have these some virtual network function, how to manage it. So possibly you can imagine you could have many instances of the same function to handle whatever load you have over your network. So for instance, I could have more instances if I have more of, let's say, an intrusion detection, if I have more traffic coming in, so that will possibly load balance or balance the load across many instances of the intrusion detection system. So you can then not have an overloaded network service there, which can, of course, impede your ability to detect quickly attacks or malicious behavior. So the idea here is that can we, in general, the issue of managing possibly one or more instances of a virtual network function. How do we do that? And we want to leverage here software-defined networking. Specifically, in this webinar or this tutorial, we're going to use OpenFlow as a way to talk to the switch to install forwarding rules to direct traffic to one or more of these instances. And we also want to leverage control theory for do this kind of balancing of the load across these instances of the virtual network function. So this is a quick overview of basically the problem that we have and what we want to do. I think I will also say that please interrupt or ask questions if you have any, or I think there is a chat room, chat kind of box that you can use to also put in your questions, and I think Ben will help me if there is such a question there. You will let me know. All right, so this is joint work with my PhD students, Nabil Akhtar and Yufeng Wang. And Nabil actually will later on, after this short presentation, will be able to give us some a quick hands-on demo for this tutorial. So the tutorial instructions are available. I'm not sure how many actually managed to go over the tutorial. It's a kind of a long tutorial, so but we hope that the hands-on demo at the end will help you get started at least. And if you had already started, it would be great. So you can ask questions later on. All right, so this tutorial, by the way, I first gave it during the summer GENI summer camp at BU here. That was the first time I gave this tutorial. So if you have been at this summer camp, sorry, I apologize. It will be a repeat to some extent of what we did in the summer camp. All right, so I'll start say a few words about control theory. I don't know how many are familiar with that. So the general goal of the control theory is given a system, how to control it so that it actually converges or reaches a certain target operating point, a desired target operating point. So this is an example, a classical example from control theory, where you have basically a tank of water. It's leaking at a certain output rate. But maybe we don't know what this output rate is. And then we have an input flow coming in. And our goal is actually to control the rate of input flow through this input valve control there to maintain a certain level of liquid or water in this tank. So the idea here is that we would like to open up the valve, the input valve, a little bit to let more flow in. If we fall below, if the water level falls below a target, otherwise we would like to shut down the input valve if the opposite is true. So that's basically the general problem in networking. In a networking setting, for instance, imagine this output flow there is actually, or the output valve there represents the capacity of your connection that is available to your connection, and the source here, let's say TCP source, is trying to control the rate at which it's sending to match this available capacity that you don't know what it is. So what you'd like is to do some measurements, and the goal possibly could be to maintain a certain number of traffic or packets, a certain amount of packets in the bottleneck router or queue, the slowest queue along the path of your connection. So you want to maintain this level by doing some measurements, let's say round trip delay measurements or one-way delay measurements to be more precise. All right, so the goal here is to maintain this level so that we don't have too many packets, for instance, that will introduce too much delay, and not too few packets, because we want to have always packets to send to maintain high utilization of the network. Right, so this is one very classical use of control theory. So in general, we have basically given a physical system that we'd like to control. We have a monitoring system or sensors to measure things like as I mentioned earlier, let's say I'm measuring the level of the water in the tank, or I am measuring the round trip delays or the one-way delays or the losses that I'm observing. And then based on that, I have the computing. So I'm going to compute some control law that will determine what's in this case, let's say the input flow rate should be. And then actually I'll do it. So you have the actuators that actually go ahead and apply that control on the system, right? So it turns out that this quote there is actually saying that most of the real-world applications that we'd like to control use basically 10% of the existing control methods and theory. So that's saying basically that you can do a lot just by using basic control theory principles and support most of the applications that are out there. You don't need to really resort to basically kind of a fancy advanced control theory. All right, so given that, we have seen actually the use of control theory in computer science. So I mentioned already TCP, for instance. So this is so control theory will allow you to develop these kind of dynamic equations that x here is the control variable, which is the input rate of the TCP connection that depends on the loss that you observe. So this is what your sensors will measure. So you have kind of increase or decrease. So you determine actually here the amount of increase or decrease in the rate based on the observed losses. Tau here you can see they can model also the feedback delay. So that's nice about control theory. You can also measure what we call feedback delay, which is delay it takes you to measure the state of the system, losses or delays, etc., and actually for the effect of your control to take place, to propagate through the network and reach the bottleneck router, basically. There is also work that has been done, so that we have studied actually different versions of TCP, and we have studied quality of service or service scheduling, server scheduling and caching problems, etc. So I have here a reference to a ACM SIGCOMM ebook chapter 2013 that I wrote that talks more about control theory and its use in modeling networks. So so it should provide a good introduction to the topic if you're not familiar with control theory. So basically the problem here that we have is I want to manage instances or a certain virtual network function or instances of it using SDN and control theory. So basically, the physical system is my virtual network functions, okay, or instances of it. And what I like to do is measure, do some load balancing across these instances. So I want to measure the load on the hosts where these instances are running. So I'm going to do that using our recursive internet architecture. So actually, we use the application management architecture of our architecture we call RINA. I will say something about it in a second. So it uses a publish subscribe system to actually, when you publish your, for instance, your CPU load information, you can subscribe to this information. And then basically, I would like to control or balance the load. So I'm going to use, let's say, a very classical standard control method, which is called PI, proportional integral. I'll say something about it later. And then basically, I want to actuate that. So the controller will decide how to balance the load. And then I have the actuator or the controller that will install forwarding rules on the switch, in this case, an open flow switch or virtual switch. So install these forwarding rules so that my traffic gets directed to the right instance, one or more instances of the virtual network function. Not sure if you have any questions so far. I'm not seeing the chat actually here, but so a use case in here in this tutorial is to use that to balance load across intrusion detection systems. So we're going to use run intrusion detection instances of an intrusion detection system, and we want to balance the load across these instances. All right, so since this is a GENI webinar, we use the GENI testbed to set up experiment or set up experiments to study issues related to that. How do we do that? So you can see I have here basically the green boxes are virtual machines. We have a controller. We have the switch. We have source hosts. We have a destination. We have host virtual machines where we are running instances of the virtual network function. Actually, if I zoom in on the VNF hosts and or virtual machines and also the controller, there is actually, we're gonna do a monitoring, run a monitoring applications across them. So I'm use, as I mentioned, this architecture that we have, the RINA architecture, application architecture, to actually run processes on the VNF hosts that I'd like to balanced load across, and also a process on the controller, so this the VNF processes running on the VNF will publish their CPU load objects with heads the CPU or load measurements. And this guy here on the controller will subscribe to this information. And then we're going to use this information, this load information, on the intrusion detection systems or instances to actually balance the load. All right, so this is, again, the test bed. So if you go over the tutorial, you can actually have the controller on a GENI rack separate from the rest of the network here, or you can have them together on the same rack or GENI aggregate. Obviously, it makes sense to have the controller closer to the network or what you are controlling. Otherwise, it becomes more challenging. So if we look at the basic control theory, it says that the feedback delay should be limited or small enough to make sure that the system is actually stabilizes or stable or converges to the desired operating point. Right. So although the controller can run anywhere, it doesn't make sense, of course, to put it at the very end of the world. Otherwise, it would be ineffective, obviously. All right, so we're gonna, so given this setup, we're gonna generate traffic. So the idea here is that we're gonna generate traffic between the sources and the destination. And what we'd like is to replicate the switch to replicate traffic to one of these VNF instances for intrusion detection, right? Once you detect intrusion, of course, the idea here is that you're gonna go back and you should install a rule, for instance, to block malicious traffic or whatever malicious behavior you detected. We will also, at the same time, would like to do that effectively. You want to balance load across instances, so traffic would potentially be replicated. So if you have a new flow, traffic flow, you can actually replicate it on and the second instance, of course. So here I'm just assuming 2 instances for simplicity for this particular experiment, but we can generalize it, of course, to more instances added or subtracted based on, again, the load on the requirements on the system or on the networks, the requirements on the network service. All right, so the VNF here, this is basically where we will have instances of intrusion detection system. We're going to use Snort, which is an open source. It allows you to detect all kinds of attacks, including port scanning attacks, application-specific behavior, etc. I mentioned already for monitoring. So now we want to monitor the load on the VNF hosts here to balance the load across them. So we're going to have this monitoring application, basically, right, that include a process on the controller VMs, virtual machine, that will read the load, subscribe to the load, and use that load information. We are using here our own architecture, our own protocol. It's called CDAP, Common Distributed Application Protocol, to exchange these objects. And just to mention something about RINA, that's another topic, but I have only one slide for it. So this is a clean slate future internet architecture. It's based on this principle that networking is inter-process communication, which is a principle that is well known, has been known for a while. You can see it in the TCP RFC here from 1981. The problem is that people haven't really applied it properly in the current internet architecture. And so our goal here in this project was to take it all the way and apply it repeatedly or recursively over different scopes of the network, or different ranges of the network. So the building block of this architecture is a communication layer, IPC layer that we call it DIF, Distributed Inter-Process Communication. So it's basically an application, distributed application with processes that provides IPC service. communication service. And then basically this building block, we can actually use it to put together, we can use it recursively to form a full network. And a DAF is basically a generalization of the diff in the sense that it's an application, it's a layer that represents a particular application. So it's processes that are doing a certain, performing a certain application like weather analytics, content delivery, etc. All right, so it's just so the diff is just a special case. It's a special distributed application that is just doing IPC. So we can again recursively or repeatedly using this building block, we can provide communication over a larger scope or range over the network and support ultimately the application or the distributed application. All right. So it's so to know more, you can visit that website, and we have also a RINA over GENI tutorial from GEC, GENI Engineering Conference 19. You can watch this YouTube video, and there is the tutorial instructions there. All right, so now, so here actually our so the RINA actually allow you to create a communication layer that this application processes that are going to do the monitoring will be running over. So they get actually authenticated first, they get assigned private addresses, etc., etc. So there is a lot of details here that are RINA specific. All right, so once we have that, this load information that we subscribe to, we pass it along to what I'll call here a load balancer. So this load balancer will decide how to use this load information to balance load. So we're gonna use here as an illustration what we refer to in control theory, basic control theory, standard control theory, a proportional integral controller. So the proportional integral controller here is just a very simple one for the purpose of this experiment. It looks at, again, considering two instances of snort, it actually looks at the load at the first instance. If it reaches a target, let's say 50%, I'm gonna start diverting new flows to the second instance, BNF, I call it here BNF2. So X here is our control variable and determines basically the fraction of new flows that should be directed to second instances of snort if the first instance again gets loaded or the target exceeds the say certain target 50%. The load exceeds a certain target. So you can see it here in this equation. So that's a simple control equation. This is just the pseudocode for it. So I'm gonna skip that. All right, so this is basically what we're gonna do. So we're gonna start the RINA application, monitoring application to monitor load. We're gonna get this load, pass it on to the load balancer, and then the load balancer now set the control variable. How much should go to the second instance as opposed to the first instance? So we're gonna pass this along to the OVS controller, which talks open flow. It talks to the switch to install the forwarding rules based on the output from the load balancer. So this is just a pseudocode that basically does that based on this value of X. Another controller that you can think of, load balancer that you can think of is easy, just do round robin. So that's one just for comparison in these experiments. So this here, every flow that comes in, we're gonna replicate its traffic to a different instance of snort in a round robin fashion. Okay, so this is basically a load independent kind of way to balance load. All right, so this is the kind of graphs that we could get actually. So here I'm having the y-axis is the CPU load or usage versus time, and the left you have the round robin. And I started actually with a certain load already on the host that is running the first instance of snort. So the load is already unbalanced, and then I start sources sending traffic to the destination. Traffic gets replicated to snorts for intrusion detection, and a round-robin fashion. So you can see that obviously, as you expect, the load stays unbalanced, right? So still have 60-40% load on the two VNF or snort hosts. If I do the PI controller, so the PI controller again starts with an unbalanced load, and then I start my traffic source destination that I would like to inspect for intrusion. And you can see that once the load on the first instance reaches 50%, I'm gonna start using the second instance. So the second instance starts kicking in and getting some traffic for inspection, and basically whatever is left. So that now the load on the first instance doesn't exceed, on average, the 50% target. Of course, you can generalize this problem, right? So here in this experiment, you only consider two instances of snort, or the virtual network function. Ideally, what we would like to do is to direct traffic to the first instance. If you reach a target, you can then start instantiating a second instance and directing excess traffic there, and so on, right? And of course, you should be able also to decrease the number of instances as the load goes down, or your performance requirements are less. All right, so this is basically part of the elastic kind of management that we are envisioning. Okay, so I'm gonna stop for a minute to just show a demo, and then before I actually hand it over to Nabil for actually a hands-on demo, is there any questions so far? Any questions? No?
Somebody
Okay,
listed a question in the chat window. Hi, Abraham. I would like to try this lab on GENI. Can you share the GENI setup scripts for these VMs and the source code of your controller? Yeah.
It's all in the instructions for the tutorial that are instructions that are posted.
So Paul,
all is there. I'll give the link at the end. End of the last slide has the link to the instructions, and it has all what you need to actually reproduce these results.
And as I said in the introduction, the slides are available on that first link in the chat window as well. So you can grab the slides there if you'd like.
Yes. All right. So this is a quick video demo here. I'm going to start from the beginning. So this is a round-robin load balancer, right? So we have two instances of snort running. This is on the top two windows here, left and right. So on your left, you have the first instance. On your right, the second instance. And the right bottom here, you can see actually the load on the first host, where the first instance is running, is already around 20%. Okay, so we are already starting with an unbalanced situation, an unbalanced load. And then I'm gonna start actually sending traffic using iPerf, which is an active measurement tool, from a source to a destination. And this traffic should be directed to the snort instances for inspection, for intrusion detection. So again, it will go round robin. So what I expect snort to receive both instances of snort. So these top windows, you can see actually the receiving actually traffic, inspecting traffic and receiving traffic. So let me start that first. I'm gonna fast forward also to help us move along here. So this is also the graphs here. So you can see that from this graph, I already have the first instance has more load to start with. And then I'm gonna now start my traffic that is being inspected by both instances. So that's being load balanced across the two instances of a snort. And if I look at this graph, I'll just move forward here. You can see exactly the graphs that I just showed you, which basically you start and with load unbalanced, the load still stay unbalanced because basically this inspected traffic the traffic being inspected is just being sent in a round-robin fashion without regard to what's the load initially going on the machines or on the hosts. Of course, if I showed you now the PI controller, which again, based on control theory, it's trying to see if to make sure that the first instance of snort is getting a load of 50%. If it exceeds 50%, I'm gonna start new flows will start being directed to the second instance for intrusion detection. So that takes into account the load. So you can see that the load eventually will be balanced, even though we start with an unbalanced situation, just to make sure it's working. So I'm just gonna show, sorry, I'm gonna go back. Let me run it. So you can see initially that only the first instance, which is the left top screen, the first instance of snort is getting the traffic for intrusion detection. And then now at this point, the load, if I look at the lower right corner here, the load on VNF1 exceeds 50%. So I start diverting some flows onto the second instance. So you'll see now the screen on your top right getting traffic, which is basically the second instance of snort. And if I look at the graph, you can see that eventually the load balances out. Actually, more specifically, the load on the first instance, or the host where the first instance is running, is at 50% average. There are some oscillations, of course, and the rest is directed to the second instance of the snort. These oscillations are actually part of what we study in control theory, right? So we want to design a controller that doesn't oscillate much, that converges quickly, etc. So there's a lot of research questions that you can answer just by running these type of experiments. So we'll go over that in a hands-on way with Nabil in a second. So just here, I'm just concluding. So our purpose here was to leverage control theory to manage these virtual network functions, also leveraging SDN or programmability that we have to direct traffic to instances of a VNF or a virtual network function. But this direction is based on control theory. So how much should go where, that's using control theory. We think control theory is useful for management in these kind of virtualized systems, programmable systems. This is just a use case. GENI is useful for this kind of realistic experimentation. We are actually running real code. We also managed to leverage our clean state architecture, RINA, to use it for monitoring. So we create a secure communication layer over which we can do a monitoring of the load. In this case, we just use a simple PI control or method, proportional integral control. And there are, of course, future work in terms of that you can look at here using these setups, how to elastically create new instances as needed, as you have more traffic, more requirements on the network service, or shrink or reduce the number of instances to reduce cost if you don't need that many. So the tutorial actually to reproduce results are here, and we have just the two versions. The one that uses POX controller, OVS controller, both are Python based. POX is one of the early ones, and Rio is a more recent Python-based, again, controller. So you can use either. Rio is the more recent, again. And we have an additional experiment here in the Rio version that includes basically attack traffic. So you can, once you get an alert from Snort, you can actually, your monitoring system detect these alerts. In addition to the CPU load, we are getting these also alerts from the Snort instances, and then we can tell the OVS controller, go ahead and install a rule to, for instance, block this particular malicious traffic or attack traffic. So this Rio version has that as well, an additional experiment at there. Okay, so that ends my presentation. We have maybe 20 minutes or so for Nabil to switch to Nabil and actually so that he can go over. Here is, you can see my the instructions here. So this is the tutorial, the POX version. If you go here, you can see the Rio version of the tutorial. You can use whatever version you want. I think Nabil is going to use just the POX version for now. All right, so I'll hand over to Nabil. So I'm going to stop sharing my screen and let him share his screen. Any questions before we start the hands-on demo?
I just wanted to clarify that you're going to just show the demonstration, and people can then afterwards, go and try it out on their own. That's the plan, right?
Yes, that's the plan. It takes a little bit of time. Of course, it takes time also to reserve the resources. So I'm not sure if any participant actually already reserved this resources. So we have this, again, this host OVS switch. We have 1, 2, 3, 4, 5, 6, 7 virtual machines, 8, 7, right? 6 and 7 the controller. So you need some time to reserve resources and go over the tutorial. So it takes about an hour or so. So we probably not feasible to do it now, but Nabil will start just so that you get an idea about what to expect, how to go, how to follow the instructions. And of course, if somebody actually already started this tutorial and they have questions, they could ask. We can, Nabil can actually stick around for beyond even 4 if someone is interested. And
There's
of course,
another question in
yes.
the chat window as well. It says, what are the advantages of using RINA distributed applications? So what are the advantages of RINA?
Right. So RINA architecture is, again, we have our the advantages that we have our own protocols, so we can actually authenticate the processes that will do the monitoring. We can initialize them with policies that we would like. So we can configure the RINA layer to actually, or processes to deal with to exchange objects that carries information that we want. So it's a more like a very clean architecture that we can use. So in this case, for instance, we are exchanging objects that carry CPU load. We are carrying the Snort alerts. You can carry whatever information, and we have authentication. We have private addresses. So it's a secure, actually, communication layer between what you would like to monitor and your controller. So whatever you want to deploy this, it will be a secure kind of communication container for your monitoring system. So that's only one advantage of RINA. Of course, there are other advantages that we can probably take some time to describe. But, okay.
Thanks.
Okay, are you ready, Nabil?
Yeah.
Okay, so I'm gonna stop my sharing here and switch to Nabil. Thank you so much again for attending so far, hanging in. Thank you. Did I switch to you?
Oh, I'm going to switch on. Can you hear me? Okay, great.
Yes.
Yes.
So what I'm going to do is I'm going to quickly go over the tutorial, and then in the end, I'm going to show. I have set up all the resources already, so I'm quickly going to show you um, the PI controller with everything on running at the back. So so this is the initial tutorial page. So here it describes briefly what we are going to do. If you go into design and setup phase, you will first be asked to reserve the resources. So you will first reserve a POX controller, then you will reserve resources in the network. You have an OVS, two source, one destination, and VNF1 and VNF2, over which we will balance the load. And as you go further, then it asks you to configure the OVS switch, where you will connect the OVS switch to the controller here. And once your setup is ready, then you are going to go to the execute part. In the execute part first, initially, just to make sure that everything is running fine, you will run a very simple forwarding a learning switch, um, the POX controller with simple learning. So this controller will basically just learn as the messages go through the network, just like a simple switch, and forward the messages. So you will run initially with ping, and once the simple controller forwarding controller is working fine, you will move forward to the NFV OVS controller. So in this part, you will first download the source code for the OVS switch to your local machine. I've already done this, so I'm not going to go over it. And then you need to configure your ports, basically telling which which interfaces are connected to VNF1 and VNF2. And once you are done with this, there are two experiments here. One is with the simple round robin that Ibrahim showed before, where you are just going to send each new flow to in a round robin fashion to the VNFs. But we are going to work on this second one, which is the load balancing using PI controller. So I'm going to go here. And so this is the PI controller. Again, we have the RINA monitoring application, which is running here between the VNF1, VNF2, and the controller. So VNF1 and VNF2 are going to share their load information with the RINA application, which is running over here. And this RINA application is then going to get this load information and feed it to the load balancer, which in our case is the PI controller. The PI controller make the decision about what fraction of the traffic should be diverted to VNF1 or VNF2, basically doing the load balancing, and give this information to the OVS controller. And OVS controller is then going to uh, put the open flow rules so that we can do the load balancing. So again, to run the RINA distributed application, you need to install Java. But I have already installed it on my machine. You will download the controller in the RINA controller, basically RINA monitoring application on the controller, and then on VNF1 and VNF2. You will put the IP addresses of controller. You will tell VNF1, VNF2 where the controller is, and then you will run the controller here. So right now we are running the RINA application on the controller basically. So let's run the RINA application on the controller. So I'm going to go here. I have all the windows already there. So this is VNF1 here. This is VNF2, just like the video that Ibrahim showed before. So this is the window which has VNF1. This is the window for VNF2, and this is for the controller. So initially, I want to run a RINA monitoring application. So I will run first. I will run the controller here. Okay. So I think the connection has expired, so I need to reset it up. Yeah. Just a second. So actually, let me quickly SSH into the controller here. All right, so first I will access the controller. I think I left it for too long, and then I'll run the RINA application here. So these are there in the instructions are there in the tutorial. I'm just going to, I probably need to SSH into all the machines again. I left it for too long, I think. So I need to SSH into these machines again. So that will take a bit of time, I think. So let's wait for a bit. All right, so I'm going to SSH here again to let's run this again actually. So I'm killing all the applications here. So all right, so initially I will let me run here as well. SSH again to 2. So now I am going to run the RINA application here. So I will run the RINA application on the controller first, and I'm going to run it on VNF1, and then run on VNF2 the RINA application. Right. So when the RINA now the RINA application is running, RINA monitoring application is running. So it's going to take some time for it to set up, and then these two guys, VNF1 and VNF2, will, after the enrollment happens, they are going to share their CPU usage information with the controller here, right? So we'll wait for some time until we see. You will see over here after some time they will start publishing their load information to the controller. So in the meantime, I will SSH into all the machines that I lost connection with, so I don't waste time there. All right, so this is fine. So here you can see in the RINA application that we are now sharing the load information. It's very hard to see, but basically these numbers are the load on VNF CPU load on VNF1 and VNF2, which is being sent to the controller, right? So now let's in the tutorial first we run the RINA monitoring application. RINA monitoring application is running, and that's fine. And now we are going to run the PI controller. PI controller is going to basically take this load information, which is this guy here, and make the decision about how much load it should be forwarding. So it will run on the controller, and it will take the RINA monitoring output to make the decision about how much load should be forwarded. So this is the RINA application running here. So now, right now, what it's saying is that there's 50% is the target load that we want to be on VNF1. We do not want more load to be more than 51%, but right now only 1.1% of the CPU is being used on VNF1, and then it will keep on doing this. The PI controller is saying just don't divert anything anywhere else. Okay. So now the PI controller is running. Now after the PI controller, we will run the snort instances on VNF1 and VNF2. So these snort instances is the IDS. Snort is the IDS which we are going to run, basically just to make sure that we generate load on VNF1 and VNF2. So I will run snort instance, one of the snort instances on VNF1 here, and another snort instance on VNF2 here. So these two snort instances, which is the IDS, running on both VNF1 and VNF2. Once the snort instance is running, and we have the PI controller running here, let's run the OVS controller. So OVS controller is going to get the information from the PI controller and make decision about where to send the information, right? So, right, it will basically install the rules, right? So let's run the PI controller. Oh, sorry, OVS controller. So I'm going to run the OVS controller over here. So now the OVS controller is running here, which is going to install the rules, right? All right, so we have everything set up here now. Snort running here. We have the PI controller running here. So let's now so the load right now, so there is also a script on the here which basically gives you live information about the load on the on the on the VNFs. You can download it and run it on the go. This is a Python version which is provided here, but I'm using the I'm using the MATLAB version. Here you can see the CPU load is around 0% on IDS, right? So let's run now run an iPerf. I'm running iPerf on destination, and now I'm going to create some load on this. So let me copy this actually. I'm going to generate some load. So I'm going to run multiple instances of iPerf. So I'm running multiple instances of iPerf. Let's see how the load information changes. So you can see it's going up. Yeah. So right now initially all the load is all the traffic is going to the first instance because it's less than 50%, as you can see here. So initially it's going, all the load is going to the first one. It's still less than 50, so let's run more instances of iPerf so we can have more load. So let me run a lot of instances. So now you can see that the load on VNF1 is more than 50%. So as you can see, it's 70%. So now, since there's a lot of load, so now we are going to divert that traffic, extra traffic, to VNF2 here. Yeah, you can see the VNF screen here to see there's the second instance is now getting the traffic also. So first instance was already getting it, but now since it's more than 50%, the second instance is also getting the traffic. Now you can see here that almost 44% of the traffic is also getting diverted to VNF2. As you can see, it's stabilizing. It's coming close to 50% here. The load on the VNF1 is coming closer to 50%, while the rest of the traffic is going to the other side here. And you can see in the load graph, which is showing you the live load on the VNF instances, that it went up, and as soon as it went up above 50% threshold, we installed the rules to divert traffic on IDS2 or VNF2, and then it started coming down, and now it's stabilizing around 50%. And you can see it's close to 50% now, while 44% of the traffic is diverted to VNF2 here. Right. So as you will see, as you move forward, it should remain here around 50%, and while the rest of it. And again, as the traffic changes, if the traffic becomes more or less, the PI controller will adjust accordingly. Okay. So this is these instructions that whatever I run here, it's already here. You can copy paste these instructions here. I just copy pasted these instructions from here, these commands from here. So that should be, I hope it should be clear. And you can also have this live graph, load graph. If you do not want to see the numbers, you can always look at this live CPU usage graph. So if you have any questions so far. There is something in the text window. All right, so I will give it back to Ibrahim.
All right, so I think that concludes the last part, which is the hands-on demo. Perfect timing, I think. 3 minutes before 4. So if you have any questions, of course, it will take some time to go over the tutorial, but of course, please email us if you have any questions, if anything is unclear, or if you are even interested in the research questions that that could come up in this kind of setting.
So Abraham, I have
Perfect.
a couple questions. So one is, if I understand correctly, you are switching. You might switch your existing flow to a different IDS system, a different SNOT system, to balance load. What does that do to the intrusion detector? Could you miss some events because you lost some of the history?
Yes, excellent question. That's a good research question. So
Okay.
far we are, yes. So far we just are looking at kind of stateless kind of detection.
Yeah.
But I agree, it is a very good point. Of course, you might have some state that you'd like to move to the new instance, possibly, right? So it's excellent excellent work to do. Yes, we so far there's this experiments that we have here. It just assumes kind of a stateless kind of detection. Yes.
Great.
Go ahead.
My second question was, looks like you have a custom image with SNOT installed. I'd forgotten you had that. Recently, a couple of months ago, somebody asked me if there was a custom image on GENI with SNOT installed. Could somebody use your custom image for other research, or is it?
Yes, they can.
Okay, great. If somebody asks now, I'll know where to find the image. Great.
Oh, okay. Yes.
Thank you.
There was a question for Nabil in the chat window. Why do the NFVs need to know the address of the controller? Was that discussed?
All right. So the okay. So what we have here is that we actually overlaid our RINA network on top of. You can overlay it on top of the internet, TCP or UDP kind of connections. So for us, these UDP or TCP connections will be like a wire, right? And we are gonna build our RINA network on top of that. So these addresses are just meant to run it as an overlay on top of the internet. But basically, what we have in RINA, actually, the communication layer that you build can have any kind of topology you want, any kind of virtual graph you can form. So you can decide who should talk to whom as a neighbor. We assign internal addresses. We authenticate, of course. So if you when you run the RINA application, you'll see actually that there is a joining process on enrollment process to the layer. So the monitoring layer that we are building. So there is enrollment and authentication. You assign private addresses. You initialize specific policies that you would like to initialize. So you form the communication layer basically overlaid on top of. So that's why we need basically these IP addresses, so that the VNF can reach the controller basically as a wire, not anything more than that. Also,
any other questions? Are there any other questions for Abraham? Okay. Well, we want to thank Abraham so much for presenting to us for the webinar, and